Hi guys, I am Saurabh Gupta. I am a student of IIT Bombay, currently studying mechanical engineering. I cleared my JEE in the year 2010 and secured an EIR of 443. I have cleared the second stage of chemistry Olympiad conducted by HBCSE. Now today we are going to study the topic alkanes. This is the advanced level of alkanes. So you will be studying some of the questions based on the theories which you have learned earlier in the basic level of alkanes. It is better to revise those concepts and study the NCERT book once. So before watching this lecture, so that you follow me in each and every question. Now in this lecture, we will be seeing some of the questions based on the properties, that is the chemical properties and the physical properties of alkanes. And definitely some questions will be there based on the conformers. We have studied the conformation analysis and we have to do some questions so that we can enhance our knowledge. And now we will go for the first question in the lecture. Actually, this alkanes topic is a very easy topic relatively because alkanes are not so much reactive. So we have a limited set of reactions and so we don't have any confusion what logic to apply or which reaction will take place. But as we go further in organic chemistry, when big compounds like aldehydes, ketones come, then there are several reactions possible and it will be difficult for us to determine the major product, but there are techniques to do that and we will do that when we go to that chapter. Now the first question is, you have to tell me, you have to give me the reason why this phenomenon occurs. Now I am going to draw a compound over here. This is a compound, small one, quite small. Now there are some double bonds present in the compound and here, no, there is one more ring and to this one more final ring is attached. As you can see, this is a mixture of double bonds and cyclohexane rings and you have this 4-membered ring also, 4-carbon-membered ring. Right now all are having aromatic character except the 4-membered ring. Even this is a benzene ring, you can say this also and this also. So right now the compound is aromatic. Now I am putting 3 hydrogens in the presence of palladium. So that means clearly what type of reaction will happen here, that is the hydrogenation of the double bonds. Now which double bonds will be hydrogenated? So that is exactly the question. You have to tell me what is the product over here. Which double bonds are hydrogenated and what is the final product. How do you decide it? You decide it definitely based on the structure of the final compound. Suppose I remove this double bond and add 2 hydrogens over here. So there will be 2 hydrogens in the cis configuration. As I have told you in the basic lecture, the hydrogenation of an alkene gives you a cis configuration. That is, both the hydrogens are added from the same side. Now if I remove this double bond and let us say this double bond. I have removed 3 double bonds and let us see what structure we are getting. We have got a benzene ring, we have got this benzene ring, but now the aromaticity of this ring is lost. This is no longer a benzene ring or it is no longer an aromatic ring, while this is an anti-aromatic structure. So one anti-aromatic structure is present and one aromaticity is lost. So that means this does not seem to be a good solution. Let us see if there is some other solution possible. What if we remove this bond and this bond? Then what we get is that the 3 aromatic rings are still as it is, but what changes have happened, that this anti-aromatic ring and this anti-aromatic ring has disappeared. That is, the double bonds are gone from there and they are now normal 4-membered cyclo rings. So that means this seems to be a very nice structure because here the stability of the molecule has actually increased. Earlier also it had 3 aromatic rings, but there was a disadvantage that we had 2 anti-aromatic rings. Earlier the structure was this way and this way. So earlier we had actually 3 anti-aromatic rings and 1 extra aromatic ring. So let me write earlier 3 anti-aromatic, 1 aromatic, 4 aromatic actually. Now After we have done the hydrogenation like this, what do we have? We have 0 anti-aromatic but only 3 aromatic. So now the advantage is that we are removing 3 anti-aromatics, and the disadvantage is we are removing only 1 aromatic. So that means this is quite a stable structure, and hence this will be the final product. So very simple question. The reaction is hydrogenation, but you can combine it with the logic of aromaticity to create a nice question, and this is a question in JEE. So now let's move on to the next question. A very simple question. This was, you have to tell me what is the product in this reaction. CH3 C MgCl, CH3 thrice MgCl, D2O. Now, what is the product in this reaction? How do we determine what is the product? We have to first see what are the characteristics of the reactant and what are the characteristics of this solvent. This solvent is normal H2O, except for the fact that H is replaced by a D over here. Now what is the possible reactions? Now first of all we need to know the properties of this kind of structure. Now this is a Grignard reagent, which is very similar to the lithium alkyl cuprates, which is R2CuLi. It is very similar to this, but except for the fact that here we have discussed this in the chorea of synthesis, the lithium dialkyl cuprates, and this is very similar to that because this is also an organometallic compound, except for the difference that here the metal is magnesium instead of lithium. So we just remove this and we can write it something like MgCl plus. So we can write it like this because we know organometallic compounds, even in R2CuLi, you have R2CuLi. When you react it with Rx, you get RR, R dash X, you get R dash. So here also R is minus charge, and this attacks this. It kinds of a nucleophilic substitution, which we will learn in the subsequent chapters. Some kind of reaction happens like this, and we get R and R dash. But the only thing we need to know over here is that the alkyl group possesses a negative charge and this MgCl part possesses a positive charge. So now what reactions can happen? Now the reaction that can occur now is this negative charge acts like a base. We have seen in the acid bases thing that this is a very strong base. This is a carbon ion, and the carbon ion is a very strong base, so it can abstract the hydrogen or the deuterium from here. So this DOD, this is an acid. We know water acts as acid as well as a base, and hence in presence of this is a stronger base than water. So in presence of this acts as a acid. So this negative charge abstracts this deuterium, and the structure becomes C, C, C and D. So this is the final structure of the compound. So what do we observe over here? We observe that this, from a Grignard reagent, this type of reagent is called Grignard reagent. We are getting Grignard reagent, we are getting a alkane. That means this is also one of the production methods of alkanes, using a Grignard reagent. Use a Grignard reagent, combine it with D2O or H2O, and you get an alkane. How are Grignard reagent produced? That we will discuss later, not in this lecture, in the subsequent lectures. But the properties of this Grignard reagent are very similar to the R2CuLi properties. So that is why I have given this question here, to understand what is exactly the reason behind that I use R2CuLi reaction with Rx. There also the R minus is possessing a negative charge, and it attacks the Rx and R dash X, and it combines to form R dash R. So this was a very simple question if you knew the properties of the Grignard reagent. Now you know the properties, now you can solve it easily. Let us move on to the third question. So these two are very simple question. Now let us do an interesting question. we have a ring here, we have OH and we have C double bond of CH3. Now this has to be converted to with that ring OH C CH3. Now the options given to you are Hg Zn HCl. Second one we have ZnH plus. Third one we have NH2 OH minus, and fourth option we can say none of these. So now this is a single correct question and you have to tell me to bring this type of transformation which of the reagents can be applied, whether this or none of these reagents can bring this type of transformation. Now this is an interesting question. Tell me quickly what is the answer. The answer must lie in the logic. And what is the logic? The logic is that here we have OH, there also we have OH, but the double bond O is missing over there. We have got a alkane there. That is, the carbonyl group has been converted to a alkane, and that is a reduction reaction. So what are the reagents that are available for us for doing the reduction reaction of a carbonyl compounds to an alkane? So let us see. First we have Hi phosphorus, Hi red phosphorus, that converts. Next we have Clemenson's reduction, then we have Wolff-Kishner reduction. So now out of these three, Hi red phosphorus is not present in these options, so but Clemenson's and Wolff-Kishner reduction are present in the options. But where? I do not see Clemenson's and Wolff-Kishner. This is the reagent for Clemenson's and this is the reagent for Wolff-Kishner reduction. Now any one of these two reagents can reduce it to that, but this is a single correct option and you have to choose one of them. Which one will reduce and or which is the better reagent, which is better reducing agent for this particular reaction. Not in general, we are asking which is a better reagent or which is a better reducing agent for this particular reaction. Now as I have told you, out of these two, sometimes you have to choose one and then we choose by seeing the reaction conditions, which is the most applicable. Now suppose I take HgZn and HCl. Yes, definitely the reaction will happen. The double bond O will be reduced to the alkane, but what about this alcohol? Because of this HCl, the alcohol, the hydrogen will be abstracted and this will slightly change the structure and this might go under some other reaction. So we won't get this product. If we want to get this product, then we maintain the basic medium and we select the Wolff-Kishner reduction, because the difference between Clemenson and Wolff-Kishner is that Clemenson is an acidic medium reaction and Wolff-Kishner is a basic medium reduction. So that means for this particular reaction, we need a basic medium so that the OH group is not affected while we reduce the double bond O to the alkane group. So that is why we choose here the NH2 OH minus reagent. So a very nice question based on a very simple logic that both can be reduced by two reagents. Which one will you choose? So this is an example of practical organic chemistry where we need to choose one or more from the list depending on the reaction definitely. So interesting question. After this, let us move on to the next question. The next question says that out of the following compounds, which gives only one product on monochlorination. Fine. The options are neopentane, second one toluene, third one phenol, and fourth one is aniline. Now, which of these gives only one product on monochlorination? Now, first of all thing, how do you get monochlorination in these three compounds? Neopentane is fine because it is an alkane, and we know that monochlorination does happen on alkanes. We have seen the reaction also, we have seen the mechanism too. But how does monochlorination happens in these cases? Let us see. If there is a phenol like this and like this, then monochlorination of this can happen, like the chlorine can replace the OH. But the point is, we are not supposed to change the properties of original compound. What we should do is probably something like this or something like this. So that will be the result of monochlorination. So as we see here, that here two different positions or even three different positions are possible. So that means definitely there are more than two products possible. There are more than one product possible. That is at the ortho position, at the para position, or at the meta position. But we will learn in further chapters when we study the aromatic compounds that only these two products will be possible. Here the only logic which you have to apply, that we have to do the chlorination, and definitely if you do a chlorination over here, that is different than the chlorination over here, because there are two different products. Similarly for toluene and aniline, if you analyze, then also you will get more than one product. In toluene there is one more product possible. Can you guess that? Definitely we have an alkane or alkyl group, and we can have a chlorination over here. That is, we can have CH2Cl. So that means one more product is possible other than the normal para, chloro and meta products. So now what about aniline? Aniline also same case. That means we get our answer is neopentane, but still let us have a check. Neopentane structure is CC, CCC and C. I am not putting the hydrogens because they are not so important. Now, can monochlorination happen over this carbon? There are no hydrogens on the middle carbon. That means monochlorination can't happen over it. What about this carbon? Yes, the monochlorination can happen. Let us draw it. What about the other three? The monochlorination can happen over here, definitely. And this has not got any alkyl group. This is a perfect neopentane. What about this? Yes, monochlorination can happen at this carbon also. What about the fourth one? Monochlorination can happen on that carbon also. But what do you observe in all these 4 or 5 structures? We observe 4 structures. We observe that all are same. I mean, it doesn't matter whether chlorine comes on this carbon, this carbon, this carbon, or this carbon. All are symmetrical, and hence the product will be same. So that is why only one product is possible on monochlorination for neo. Let's move on to the next question. The next question says, which of the following is or are the correct Newman projections of 2,3 dimethyl butane? So that means this is a multiple correct question, because it says which of the following is or are. So let us first write what is dimethyl butane. 2,3 dimethyl butane. Now the structure of that would be CCCCCC and 2,3. Fine. Next, we have to first draw the Sawhorse projection, because then only we can draw the Fisher projection. So drawing the Sawhorse projection definitely will be something like this. Suppose I start with this carbon. Anyway, you can start with any other carbon, then this carbon, and then next carbon, but having a chlorine or having a methyl group. So this carbon is something like this, CH3, and another carbon is, again I will draw in blue. It also contains a CH3. We right now don't know what is the configuration, whether it is anti-Gaussian or staggered. We don't know anything, so we can just draw it randomly. So another hydrogen, hydrogen, hydrogen. So in whichever I have not mentioned any group, that by default is hydrogen. Fine. Now it's time to draw the Newman projection. So the Newman projection is first the three groups, and then this group, and then this group, and then this group. But the question says you have to draw the Newman projection about the C2-C3 bond. And what is the C2-C3 bond? 1, 2, 3, 4. So this is the 2 and 3 bond. So that means first comes the black one. Let me give you your options also. The options are CH3 and HCH3. Then we have one thing like this, CH3H, H. This is our first option. The next option is CH3. We have CH3, 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 H, CH3, and we have H over here. Okay, and yeah, CH3H, H. Fine. The other option is CH3, CH3, H, CH3, CH3, CH3. Finally, this is the fourth option, which says CH3, then we have CH3, H, but now it is an eclipse conformation. So this is CH3 and O, CH3, then we have CH, H, and finally on that side we have CH3. So we have got CH3, CH3 eclipse and HCH3 and HCH3 in eclipse. Fine. Which of these Newman projections are correct? Now to identify that, first of all let us see whether at least it is a Newman projection of 2,3 dimethyl butane. As we have seen, this contains how many carbons? 1, 2, 3, 4, 5, 6. So if the Newman projection contains less or more than 6 carbons, that means definitely it is wrong. 4 plus 2 is 6, and let us start from here. Here we will have 2 carbons across which you are writing the Newman projection. So 2 carbons. Other carbons must be visible as the groups. So 1, 2, 3. So that means at least we can say that this structure is wrong, because there are only 5 carbon atoms. 2 carbons are present because as a dot and as a circle, that are 2 carbons, and the other carbons must be present as the groups. What about here? Here I think it is correct because we have 4 carbons in the groups and 2 carbons as a dot and the circle. Here also there are 4 carbons, and here also there are 4 carbons. So that means we have to select our option out of these 3. So let us start writing the Newman projections about C2-C3. First let us try to write the eclipse projection, because this is the eclipse, other two are staggered, and we have to see the staggered which one is correct. First let us write the eclipse one. So if we write the eclipse one, CH3 is the black one, then we have hydrogen, then we have this group also is CH3. Fine. Now we have to draw the blue circle for the blue carbon. Now we have one hydrogen, which is in this case we have to draw the eclipse structure. So that means all the bonds of this must be eclipsed with the bonds of this. Yes, I think they are quite eclipsed, and according to this hydrogen is eclipsed with the CH3. That CH3 we have drawn on the top. So this hydrogen goes and merges with the CH3. Now this CH3 is in eclipse with this hydrogen. So we have a CH3 over here, and finally we have this CH3 group which is on the back in eclipse with this CH3 group. So now let us see whether this structure matches with this structure. Definitely it matches because CH3 with CH3, CH3 with CH3, HCH3 and HCH3. It doesn't matter whether it is at this position or this position or this position, because you see that the CH3 CH3 is on the top and here the CH3 CH3 is on the right hand side or the left hand side. But the thing is, this structure can be rotated to get this structure, and we know rotation about single CC single bond is allowed, and hence it can be, this should be the correct structure. So let us put a check mark there that this is a correct structure. Now let us compare the staggered forms. Now if these two are the same Newman projections for the C2C3 bond, staggered bond, so that means this structure must be coming from this structure, or we can get this structure through rotation of C2 over C3. Let us see whether it is possible, so that at least we can get that either both the structures are correct or one is correct and one is not correct. It might also be possible that both are wrong. So if we have CH3, 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 let us see, we don't have CH3, CH3, CH3 on the single carbon. Here you see that the three CH3 groups are present on the front carbon, because you see these bonds are visible. That means they must be present on the first carbon on C2. But this structure says that the first carbon or the C2 carbon consists only two CH3s. So that means either this structure is wrong or this structure is wrong. But we can also judge that by drawing the staggered form. Now we know this is the correct eclipse form which we have drawn over here based on this structure, this Sawhorse projection. That means we can rotate the C2 carbon and try to get this structure or that structure. Now to make things simple, we note that on the front carbon, that is at C2 carbon, there are only two CH3s, and hence this structure is wrong because there are three CH3s on the front carbon. Fine, that is checked, that is done. Now let us see whether this structure is same as this structure. Now if you draw the staggered conformation for this, let us see the orientation which matches. If you see the blue bonds, the back carbons, two CH3s are like this, one hydrogen is like this. So I will just rotate the back carbon in this direction such that the CH3s come in this way. So I will rotate the back carbon such that CH3 comes over here. So I will rotate by 120 degrees. CH3, this I rotate, I get CH3, and this I rotate, I get hydrogen. But there is a problem. Okay, this CH3 goes on top. This is the CH3. Now this CH3 comes over here and this hydrogen comes over here. Fine. I have rotated the back carbon. Now let us try to rotate the front carbon so that this structure comes as the conformation of this structure. That is the eclipse and this is the staggered one. So the back carbon configuration is matching because you see the bonds which are not visible, two CH3s are like this and one hydrogen is this way. Oh, it is still not matching. That means we need to rotate it further. So if we want to rotate it, you can rotate it this way. You can make it with the blue marker. You can make the CH3s this way and this way. So now you see that the back carbon configuration is exactly matching. Now let us rotate the front carbon. Front carbon, if you are rotating, this one CH3 should come on the top. That is already on the top, and one CH3 is on the right. So let us rotate it in this direction. So if you rotate it, this CH3 comes here, this CH3 goes here, and this hydrogen comes over here. So now this does not seem to be the same structure because even if you rotate this CH3 like this, if you rotate this CH3 and bring it over here, this CH3 goes over here and you don't get the same structure given by this. Let us, if you want to try this out, you will get that this CH3 are not matching. That is, this CH3 is not dividing the CH3CH bond as same as given by this structure, because if you want to write this type of structure through this, you will get what? Let us see. This CH3 is there. Now this CH3 is over here. This CH3 is like this, and this CH is something like this. And you see that you have a CH3 like this, CH3 like this, and a H like this. Even if you rotate, you get it. Fine, you rotate it by 120 degrees in the clockwise direction and you get the answer. This is correct. Fine. So a very simple question based on the Soh's projection and Fisher project and the Newman projection, and we know that the eclipse conformation can be converted into the staggered conformation by rotation of the carbon-carbon single bonds. So this is done. Let's move on to the next question, which is a question on chlorination. Now the question says that there is a compound and you have to find out how many isomers are possible if that compound is monochlorinated. Now that means that you need to find out the stereoisomers also. So we have one carbon like this, another carbon like this, one carbon like this, another carbon like this. Fine. Now this compound is actually monochlorinated, Cl2 and H nu. Now if this compound is monochlorinated, you need to find out how many isomeric structures are possible. We know that when chlorination is done, many isomeric products are possible and they come in different ratios. Here they are just asking, write the structures of all the isomeric products. Let us start. If you put a Cl over here, now if you put a Cl over here, what we get is this is an isomeric, or this is a chiral carbon. So now this is a chiral carbon and we get a Cl over here. Fine. So we get one product. Next, if you write another product for this, then you can have a Cl over here through monochlorination, and that also means that this carbon becomes a chiral carbon. And 1, 2, 3, yeah, 1, 2, 3. So that means we get another product. Now what else? Now the middle carbon can also be chlorinated. Let us do that. So we are chlorinating the middle carbon, but now none of the carbons become chiral and we get only one product. So this is the third product. Now you should ask me why I have written when these two become chiral carbons only one products. That is because we are getting these two products because of the chlorination on the adjacent carbon. If the chlorination was on this carbon, which is supposed to become the optically active, then we would get the two products. Actually, when this becomes optically active, this is the enantiomer of this carbon. So now we move on further chlorinated. So if you should understand that concept, that because the chlorination is done on the adjacent carbon, we don't get two products over here, we get only one product. Now we chlorinate this carbon. Now this carbon again becomes optically active. There are no geometrical isomers possible and conformers are not isomers. So that means this becomes optically active and now you get two products and totally it becomes 5 products. So you see that when the chlorination is done on the same carbon, then it can have two positions. It can attack from top, bottom. So there are two configurations and they give the two enantiomers. So there are two products. And finally we chlorinate this carbon and this carbon, which is residue, this and this, and we chlorinate this carbon. We again find that that carbon becomes optically active and this carbon becomes optically active, which gives us two products, totally 7 products. And next, the final carbon we have to chlorinate, but you have to check that that carbon, whichever compound we are getting, that is not similar to any one of these carbons. So any one of these compounds. Now let us see this, and we chlorinated here. Now compare this and this. Here it is a 1, 2, 3, 4, 5 carbon chain with a substitution at the 1, 2, 3, 4th position, and here we have 1, 2, 3, 4, 5, but the chlorination and the substitution is at the adjacent carbon. So that means this product is different from this product, and definitely that product will be different from this product, because now this comes in the main carbon chain 1, 2, 3, 4, 5. This is one product, and this substitution at the adjacent carbon to it. Now let us again verify that we don't have a repetition. This carbon also a 5 carbon atom, 5 carbon parent chain, 2 substitution at the second carbon. Fine, same, this product is not same as this. What about this? In this case, you see that the chlorination, the products of the substitutions are at the 2 and the third carbon, 1, 2, 3, 4, 5, sorry, the third and the fourth carbon. Third and the fourth carbon. And this is definitely not same as this structure, but this is same as the second and the fourth carbon. So you see that all the products are different, none of the products are identical, and hence, and here we do not get any optically active carbon, because none of them becomes optically active, we get only one product. So 1, 2, 3, 4, 5, 6, 7 and 8. So totally with monochlorination we get 8 isomeric products. This is a huge number. A simple compound, a simple 2-methyl pentane gives you 8 products on monochlorination. Very nice question and a very challenging one, because people are definitely supposed to make mistakes over here. They will consider that because of this chlorination you are getting 2 products over here, and because of chlorination you are getting 2 products over here, so they will make it 10 products. But you don't do that mistake. This can be a very good numerical question, which is nowadays very, very common. So now we move on to the next question after this interesting one. Now the next question says that what? That an alkane C6H14 gives 2 monochloroalkanes when chlorinated. That means there are 2 isomeric product forms. Now the previous question was you are given the alkane and you have to calculate how many isomeric products it can form on chlorination. But here now the question is you have to identify that what is the structure of the alkane given that 2 isomeric products are forming. So now what we do is we start our search. 1, 2, 3, 4, 5, 6. This is what? Hexane, and if you want to chlorinate it, chlorination, as you know, is not such a selective process. That means it abstracts 1 degree hydrogen, 2 degree hydrogen as well as 3 degree hydrogens. So we can have a chlorination over here, we can have a chlorination over here, and we can have a chlorination over here. So that means there are 3 possible isomeric products. What about this compound? 1, 2, 3, 4, 5, and suppose we have a methyl group over here. And we know that how many isomeric products are possible? This and this. For C6H14 there are 5 isomeric alkanes. C6, 1, 2, 3, 4. Then we can have a double substitution over here, or we can have 1 and 1 over here. So these are the 5 products which are 5 isomeric alkanes. Now we have to see and monochlorinate them. Now here 1 chlorination can be here, 1 chlorination can be here, but let us now check whether this product is same as the earlier one. Now here the main carbon is 1, 2, 3, 4, 5, that is 5 parent carbon chain and substitution at the second position. What about this Cl? Here also we have 1, 2, 3, 4, 5 carbon chain and substitution at the second position, but we need to check that this does not become that enantiomeric carbon. So let us put a star over here. Now we see that again this gives us one product. So this is actually giving us two products because chlorination can happen over here and the chlorination can happen over there too. So if we are just supposed to consider the structural isomers, no, this is not giving you two products. This chlorination is actually giving you one product because structurally they are same but optically they are different. Fine. And so one chlorination over here. What if the chlorination happens in the middle? Yes, that is also a possible product. And definitely chlorination over here is possible. That's it. And chlorination over here will also be possible. So because of this methyl group which is present over there, that gives us so many products. So this is not our answer definitely. We need not even bother how many isomeric alkanes are possible or how many isomeric products are possible. Coming to this case, we have this, we can have one chlorination, second chlorination, and definitely we can have a chlorination over here. So that means this is not our case also. So finally, which is our answer? Let us see for this. One chlorination over here, another chlorination over here. So these two are the possibilities, and you see that this chlorination will give you the same product, and no, this chlorination also will give you a different product because these are the third position, the two dimethyl groups, and in this case it is on the fourth or the second carbon. Fine. So our only option is this product. Let us see one product over here, one product over here. So that means this is our answer. You can see that there are no products, no other products possible, and it also does not become optically active. So only exactly two isomeric products are possible for this structure. So we see by doing so much of exercise, we have to see whether the isomeric alkanes is giving two structures or more than two structures, we get to that answer. Fine. Let us move on to the next question. Now the next question is actually a multi-correct. Sorry, it's actually a match the following. The question is match the following. There are 4 questions and 4 options. Match. I'll first give you the 4 options. The 4 options are configurational diastereomers, configurational diastereomers. Second one is conformational enantiomers. Third option, conformations. And fourth option, configurational enantiomers. So as we have seen in the basic lecture, that it is possible to have enantiomers both in the configurational as well as in the configurational way, conformational way. So let me give you now the options. The options are, I will give you the Newman projections, you have to tell me the answer. OH, H, and the back carbon, it says OH, H, and COH. The second option is the second pair, COH, OHH, and at the back COH, OH, and H. COH, OH, and H. Now as we see that this is a Newman projection, and we are asking the relationship between the Newman projections, diastereomers, enantiomers, etc., etc. And we have seen earlier that these relationships are determined by the Fisher projections. So that means our task is to convert these Newman projections to the Fisher projections. So let us start converting. First, what we need to do is we need to draw the eclipsed conformations of these. So we will just rotate it such that the blue carbon I will rotate. So COH, H, OH, and then the blue carbon is H, OH and COH. This is the eclipse conformation. Now we draw the Sawhorse projection from this. So the Sawhorse projection, the blue carbon is at the back and the back carbon is at the front. COH, HOH, this is the carbon bond. The blue carbon says that H is parallel to COH, and then we have OH, and finally we have COH on that parallel to black H. So from this, now we write the Newman, from this we write the Fisher projections. Fisher projections, we need something, the top and the bottom. So these bonds will come in the plane, and the COH and COH will come on the right side and the left side respectively. So we draw it over here, that H and H, like this way, the COH, and we have COH, OH, and we have H and OH. H is on the same side as the COH, OH is on the same side as the COH and as the OH. So finally we have got the Fisher projections for this Newman projection. Similarly, if you write down the Fisher projection for this, and let us find out the configuration for this Fisher projection. Now here the thing is, this lowest priority group is at the back. Who will get the first carbon? Then first priority, this is the second, this is the third. So now this is the anti-clockwise direction, so it will be S. The correct configuration of this carbon is S, and similarly you can determine the nomenclature for this also. But we are not going to follow this method. We are going to write the Fisher projection for this Newman projection and then compare them instead of just giving the nomenclature. So we need to draw the eclipse projection of this. So I'll keep the black one safely like this, H and OH. Then the blue ones I will draw to make it eclipse, COH, H, COH, and we can see OH this way. Now we convert it into a Sawhorse projection. COH, OH is the same. Now the only thing is the OH and COH is changed. OH and COH. Now if you draw the Fisher projection for this, what do we get? We get that, I will draw the Fisher projection over here. For the first carbon, it remains the same, HOH and COH. Sorry, the first carbon is this carbon. So for that it changes, because now the COH is on the right and the OH is on the left. So the basic rule for changing the Newman projection to Fisher projection is, you take the eclipsed form and then convert it into the Newman and then convert it into a Sawhorse, so that you can easily write the Fisher projections. So now OHH we have drawn this way, OHH and COH. So now tell me, what do you observe in these structures? We observe that the configuration of this carbon is exactly the same, but the configuration of this carbon is reversed. So that means, suppose this is S, then this will be R, and it will be some X, this will also be some X. X can be R or S, it doesn't matter. So now that means these are two diastomers, and these two diastomers are coming due to what? Configurational changes. We have exchanged this H and OH, and to bring that configurational change, we need to break the bonds, and we require a lot of energy. So that means the correct answer is configurational diastomers for the A1. A is the first one. Next what we see is the second Newman projection, which is COH, HCH3, and at the back we have CH3 H and H. CH3 H and H. Fine. This also we have to change. This arrow we can remove. Our question says that on the front we have HHCH3, HHCH3. On the back we have got CH3COH and H. CH3COH and H. Now these two conformers we have to identify whether they are conformers or conformational enantiomers or configuration enantiomers or configurational diastomers. Now for that, just observe the back carbon here consists of CH3 H and H. Now here the front carbon consists of CH3 H and H, and here the back carbon consists of and the front carbon consists of COH CH3H, and here the back carbon consists of CH3 COH H, and the staggering is exactly the same. That is, this CH3 is between CH3 COH, CH3 is between CH3 COH, H is between HHH, and similarly you observe the COH also. That means what clues does the structures give to you? What can be the possible relationship? See, the Newman projection is seen along a CC bond, that is 2,3 bond. It can be even 3,2 bond, that is, you see the Newman projection along this line, or you see the Newman projection like this. What will you get? You will get just the opposite of this, that is, whatever groups are at the back, they will come at the front, and whatever groups are at the front, they will go at the back. So actually they are the same or the same conformers of each other. They are identical. So the answer must be 3. B is 3. You cannot say that these two are identical because they can be conformers of each other, but at least you can say they are not any diastomers or enantiomers. Enantiomer and diastomers are not possible because here we don't have any, except for this carbon it is not chiral. So either they have to be enantiomers or they have to be identical, and we find out that these two are actually identical. Fine. Now we move on to the third question. Now this question says, now this is a very familiar question to you, at least those who have seen the basic lecture, it is a very familiar question. Here we have Cl on the equatorial side and we have Cl on the other equatorial side, and the other conformer which we have is this type of conformer where this goes like this, this goes like this, and now the Cl is actually this way and this way. Now what is the relationship between these two conformers? Now first clue that you must get is, this is supposed to be something familiar to the ring flipping case, because when you flip the ring it gets the shape of this ring, but you need to be pretty sure that this is indeed the case. This is indeed the case of ring flipping, and we have seen in the basic lecture that this is the 1,2 trans dichlorocyclohexane, and which shows conformational enantiomerism. That is, these two are enantiomers of each other, although these are just the conformers. That is, we can get enantiomerism just by changing the conformation. We need not even change the configuration. The energy required to convert these two structures into each other is so less that these are conformers instead of configurational enantiomers. So if you want, just see the basic lecture for the explanation how we can convert this into this, and these two are enantiomers. So our answer is for the C, conformational enantiomers. Let's see the final question in this match the following. That is a Newman projection, which is like CHO is on the front carbon, HCH3, Then on the back carbons we have NH2, H, and we have another hydrogen. Now on this carbon again we have CHO, we have CH3H. Then on the back carbon we have HNH2H. HNH2H. Fine. Now we have to determine what is the relationship between these two. Let us try to find it. Again, following the same procedure. First write the eclipse conformation. CHO, HCH3. On the back we have H, NH2, and we have H. Fine. If you write the source projection, the source projection is, we have CHO on the front, then we have on CH3, and then we have H. Now at the back we have H corresponding to CHO, NH2 corresponding to CH3, and we have H corresponding to H. Fine. Now we are ready to write the Fisher projections, because for these type of comparisons Fisher projections is the best way. So let us see Fisher projections. It is like CHO, we start from H, NH2 is on the right, this H, and then this CH3 is on the same side as NH2, hydrogen, and CHO. Fine. Fisher projections, as we know, is the planar projection, so we just compress the molecule. Now we need to write the Fisher projection for the other one. So CHO, H, and CH3 are just opposite, so we will just put this H over here and CH3 over here. What about the relative configurations? If we rotate, H corresponds with CHO, and this H corresponds with this H, and this NH2 corresponds with CH3. So correspondingly we will make the changes over here. Here H is on the top, H is like this, and NH2 is coming over here. So H, NH2, and correspondingly for H we have CHO, H we have CH3 over here, we need to make it H, and we have with NH2 CH3. With H we have CHO, with this blue H we have the black H, and with this NH2 we have CH3. We need to write it in black, H and CH3. Fine. We will make the same changes over there. So this blue, H on top, H over here, NH2 over here. Then we have what? CHO, and H over this side, and CH3 over this side. So what do you observe? If I take a mirror plane over here, I get that these two are exactly mirror images of each other. NH2, NH2, CH3, CH3, and 2H on the other sides. So that means they are configurational enantiomers. So you see, this is the very long journey. You have to convert Newman projection to Sohaus projection. For first, Newman projection to eclipse Newman projection to Sohaus projection, and from here you go to the Fisher projections. So we have seen the relation between all these three types of projections. Finally, we will end the lecture with a small comprehension. So the final question of this lecture is a comprehension. We will have 3 questions and we will try to answer them. Now this comprehension is based on the stability of these conformers. The first question says, which is the correct PE diagram for propane? What is this PE diagram? PE diagram is nothing but you compare the stability of the conformers, and hence we will get different potential energies, and hence different stabilities. So for propane, first let us see the Sohaus structure. anything, everything is hydrogen. So the Sawhorse projection is something like this. This is the propane diagram or the propane Sawhorse structure. Let us draw this thing, the Newman projections. If you draw the Newman projection, we need to select a bond. Let us consider the C1 and C2 bond itself. So on the front we have with the black 3 hydrogens, but on the back we will have some blue color. Blue color, and this hydrogen matches with this hydrogen. This hydrogen matches with this hydrogen, and we have a CH3 like this. So we have drawn the eclipse Newman projection for the propane molecule. Now for propane, this must be the least stable structure, or this must correspond to the maximum potential energy. Now we have to draw the correct PE diagram for this propane. So let us try to draw it. The other structures what we can draw are the first, let me draw the front ones. Front, let us keep constant. We have hydrogen and hydrogen, but on the back, when this CH3 comes over here, that is a staggered configuration. The repulsions are quite less. So when the CH3 is at the staggered position, the repulsions are lessened and we have a different energy. Fine. Can we draw any other conformational structure other than these two? Let us see. When this CH3 corresponds to this H, we will have the same structure as this. The repulsions, the steric strains, everything will be the same. So hence that conformation is not actually a different conformation than this conformation. Again, when CH3 comes over here, we have the same type of repulsion, because the field in which CH3 is there is that it is either between two hydrogens or it is between overlapping with another hydrogen. So that means there are only two possible energy levels. One will be the, so if you draw the potential energy, one will be the maxima, another would be the minima. One will be the maxima and minima. So the diagram would be something like this. Compare this with the diagram of butane. Butane, we had something like this, another minima. Now this maxima was lesser than this maxima, then again it went down, and again it came up, and it came something like this. So there were two different minimas and two different maximas, but here we have only one kind of minima and one kind of maxima. It is very similar to the structure of ethane. We have a very similar diagram for ethane also. So this was the first question. We have directly calculated what is the correct potential energy diagram, and even if I give you the options, you can match them correctly. Fine, let us move on to the next question. The next question says that the Newman projection formula of 3-hydroxy-propanol. What are the reasons for the stability of this structure, Newman structure? Let us see. 3-hydroxypropanol, what is propanol? Propane with an aldehyde group. This is propanol, and 3-hydroxypropanol means there is a OH over here. So that means first we need to draw the Sawhorse projection. Sawhorse projection would be on the front carbon OH, and the other two are hydrogens. On the middle carbon, two hydrogens, and on the back carbon we can take this 2 carbon itself and this group as CHO. So in fact we can draw the structure like with the blue and CHO like this. Fine. So now what is the reason for the stability, for the most stable conformation of this structure? What is the most stable conformation of this structure? Let us try to identify. For the black carbon, I will put one OH, H and H. And for the blue carbon, we have a CHO, H and H. Now what do you think is the most stable configuration of this Newman projection? Actually the most stable configuration should be when this CHO is anti to the alcohol group. Because of the van der Waals repulsions, there is no torsional group. Clearly, because to reduce the torsional strain, we need to have a staggered configuration. Fine, we have a staggered configuration. Next, we need to remove the van der Waals strains also. So, in order to do that, what we do is, we keep the CHO over here and draw a structure something like, if I draw the black ones, hydrogen, hydrogen, then we have CHO, hydrogen and another hydrogen. Now, tell me, oh, I have not changed the structure. CHO, hydrogen, hydrogen and yeah. Now, this is the anti-configuration and here the van der Waals strain is the least. But here there is one special property which we are not seeing. The special property is the hydrogen bonding. The intramolecular hydrogen bonding between the CHO carbon, the CHO oxygen and the alcohol carbon. There is a huge amount of hydrogen bonding and hence this structure becomes more stable than this structure. So the reasons are actually that minimum van der Waals strain is although not present, we have minimum torsional strain and we have intramolecular hydrogen bonding. Intramolecular hydrogen bonding. So minimum van der Waals strain won't come over here because that is actually not the reason for the stability of this structure. That is actually destabilizing this structure. So that means that van der Waals strain will not come in the reason for this. So a very nice question to explain that hydrogen bonding can be present anywhere. It can come in acids and bases, tautomerism, everywhere. Even in the Newman projections, you can have hydrogen bonding. There is a very important role played by hydrogen bonding. So now as a final question of the lecture, let us consider 4 Newman projections and let us try to determine the stability order. The first Newman structure is CHO on the front carbon, then we have HH, and on the back carbons we have NH2 and H and H. Then we have on the front carbon CHO and we have H, H, back carbon HH NH2 and we have CHO HH. We have on the back carbon NH2, hydrogen, hydrogen, and we have finally CHO, eclipsed one. But here the difference is we have NH2 over here and we have hydrogen over here, and here it is hydrogen and hydrogen. Fine. Now out of all these Newman structures, which do you think is the most stable and the least stable structure? Obviously the least stable structure must be this one out of these two, because these are the eclipse structures and we can find out which of these two eclipse structure is the least stable structures. Now in this case we have only hydrogen-hydrogen repulsions, but here we have hydrogen-hydrogen but NH2 hydrogen repulsions. So that creates a very big difference. But you can argue that this CHO and H difference can also be determined, because this difference and this difference, the repulsion between these two and these two groups, and here we have repulsion, lesser repulsion between hydrogen-hydrogen, but lot of repulsion between CHO and NH2 groups. But in fact, this repulsion actually outweighs the two repulsions that we are getting over here. So this is actually the least stable structure. Now the most stable structure would be what? Obviously these two, but this is the most stable structure. Why? Because again of intramolecular hydrogen bonding. Here although we have anti-configuration, same as the previous question, but again anti-configuration, there is van der Waals strain, But intermolecular hydrogen bonding is actually almost equal to a bond, a single bond. But van der Waals strain is just a normal strain. So that means the hydrogen bonding outweighs the van der Waals forces and the van der Waals repulsion forces, and hence the first structure becomes the most stable structure. Now let's move on to the next question, which is a simple single choice question, which says that which of the following is correct potential energy diagram for the chain propagating step, which is given follows. Which of the following is the correct answer for the chain propagating step? You remember what is a chain propagating step? I will just mention that CH3H plus F radical gives you CH3 free radical plus HF. Now some data is given to us, that is bond energy is equal to 435, bond energy equal to 569 for HF, bond energy equal to 569, and we have delta H naught equal to minus 134. Okay, so this is the data given to us. Now the options which are given are, this is of course the potential energy, this axis we draw the reaction coordinate. Now the potential energy diagram, the first one is CH3 free radical plus HF, then delta H equal to delta E activation, then we have the initial CH3 CH4 plus F free radical. The second option, which says the diagram is something like this, and we have CH4 plus free radical, and on top the transition state which is involved here is CH3H F radical, a bond formation is happening, then we finally get CH3 radical plus HF. The third option is the potential energy diagram starts like this, goes up and then comes down, and these three are obviously, one is the radical, one is the reactant, one is the product, and this is of course the transition state. So out of these three options we have to select which one is the correct potential energy diagram. First of all, think what is a potential energy diagram? Potential energy diagram is actually a plot for a reaction. On the y-axis we plot the potential energy. Every molecule will have some potential energy, that is what we plot them, and it is relatively. You cannot determine the absolute potential energy, so it is just some relative quantities. We have given no markings here. Then this is reaction coordinate. Reaction coordinate is the coordinate of the molecule as the reaction proceeds. Initially, when the reaction was not happening, or when this chain propagating step started, the molecules which were present in the reaction mixture were of the kind CH4 plus 1 F radical. But as the reaction proceeded, the molecules converted into a CH3 free radical and a HF molecule. So we have to determine what is the correct potential energy diagram relationship, how the potential energy of the molecule changes. Fine. First of all, think which of these plots, what is the difference between these plots? These plots, the difference. Now here it starts from here and it ends over here. That means there is no peak in between, there is no energy barrier from the reactant while going to the product. Now what is this? This is partial free radical. This is called a transition state. Every reaction, every step in the reaction, we can say, has a transition state. It has to go through a transition to get to the other side of the barrier. This is the energy barrier, you can say. Similarly, here is the energy barrier, you can say. But in this case, there is no energy barrier. that means this must be so unstable that it immediately converts into this. That is why there is no energy barrier. Is it so? That this is so much unstable that it converts very freely into this? No. On the other hand, if the reverse was happening, for example, if CH3 free radical was converted into CH4, any free radical is very unstable as compared to the neutral species. So that won't have any transition state. The potential energy diagram for that, for this such kind of processes, would be just initially the potential energy would be high and they just come down. There is no transition state and hence there is no peak. Because why the transition state involves that peak? The simple reason is, when a molecule is being converted to something else, it requires an initial energy or initial momentum so that it can collide with other molecules and the reaction can take place. So that is why this energy gap is required. It has to go from here to here, so that much energy is required, which is also called the energy of activation, and then it proceeds and it undergoes the reaction. So if it were a free radical getting converted into a neutral species, this is the potential energy diagram. You start, the potential energy of a free radical will be higher than that of the neutral species, agreed? So it must start from the top and there is no transition state in case of conversion of a potential of a free radical to a neutral species. So the graph just like that comes down. Fine. Now this is definitely wrong. Why? Because although yes, it is true that this is stable and this is unstable, so that is why the potential energy gap is there, but there will be a peak in this case because the graph cannot just like that end over here without any transition state. So that is why this can't be our answer. We will just cancel it off. What about this and what about this? Fine. Now this graph says that our initial reactant is much stabler than this one. So which in fact is wrong over here. Do you think that F radical and this CH3 radical, out of these two, which is most unstable? CH3 radical is more unstable or F radical is more unstable? The CH3 and CH4 and HF, they don't determine the stabilities when there are free radicals present. That is why we consider only the stabilities of the free radicals here. So the concept behind this question is, one, you should know what is the more we should know, have information about the stability of the free radical. Second one, we should have information about the potential energy diagram. Information about the potential energy diagram, I have told you what do they represent and how we can draw them. So now the second point, stability of the free radical. Obviously the stability of the free radical will determine which is more unstable. The reactant is more unstable or the product is more unstable. Here in this case, the reactant is more unstable than the product. So that is why our potential energy diagram must start from top and come from bottom. Now the only thing we have to decide now, which is left, is whether it will have a transition peak. If it does not have a transition peak, then the graph must be something like this, and that is not given in the options. But this graph, just the opposite of this graph would be the answer, because here in this case our reactant is more stable than our product, but just the reverse is given in the question. Our reactant is more unstable than the product. So that is why our graph should actually start from a higher position than the product. So okay, you might have a question that if this represents the potential energy and this is higher potential energy than this, so how is it unstable? Higher the potential energy, it is always unstable. The potential energy should be minimum. Why? Because every system wants stability. So that is why lesser the potential energy means more the stability. So you should not have the confusion that this is higher, so this is more stable. Actually it is more unstable. Fine. Now let us see, this graph is obviously wrong, it starts from bottom and ends at the top. Let us look at this. Now here, it starts from top, ends at the bottom and has got a transition state. Why? Why not just a graph simple downward sloping? That is because it is not instantaneous reaction. Some bonds have to be broken, some bonds have to be formed. Here also you can say that some bonds have to be broken and some bonds have to be formed. No. Here just one bond has to be formed between another H radical. That's it. And here this bond has to be broken and this bond has to be formed. As this transition state shows, the transition state is actually correct. A delta radical and F delta radical. This bond is forming, this bond is breaking, this bond is forming. That is why we have a peak over here. The bond breakage requires some amount of energy. Bond formation does not require. Bond formation on the contrary releases energy. That is why our graph is going down, because of the bond formation. How? And we can also decide through this fact. You see, bond energy is difference. Here that bond energy is higher than this bond energy. So our energy will be released. The difference of the energies will be released, and that will actually be used to break this bond. So that is why we have got a transition state, and that is why we have a peak here. So a lot is to be learned from this question. Please rewind the lecture to understand carefully each and everything in this topic. Fine. Now the last question for the lecture, it's an assertion reasoning type, a very simple question in fact. If you have seen the basic lecture of this topic, then you will be able to answer very easily. If not, also you can just learn from it. It's a comprehension. So the comprehension says, as we all know, it consists of two statements. Statement 1, N-butane on heating in presence of AlCl3 gives isobutane. N-butane on heating with AlCl3 gives isobutane. Statement 2 says that N-butane and isobutane are isomers. N-butane and isobutane are isomers. Fine. Let us look at the correctness of each question, each statement. Statement 2, N-butane and isobutane are isomers. N-butane is this, isobutane is this. So quite obviously they are right. The statement 2 is right. They are isomers. Correct. So our second statement seems to be correct. What about the first statement? N-butane on heating with AlCl3 gives isobutane. Is it right? I think so. If you remember the reaction isomerization in the end of the lecture on alkanes, the foundation level on alkanes, then you will see that this is a very obvious reaction. It is isomerization reaction which happens in the presence of anhydrous AlCl3 with HCl along with heat. So it is a very, very simple reaction. If you have seen that lecture, then this question is very, very easy. But the question is not over yet. We have decided that these two are correct statements. So that means our answer is either A or B, or depending on the instructions on your question paper, the options. But which one, A or B? That depends whether the statement 2 is the correct explanation of the statement 1. Is it? I don't think so. Because the answer should be, because it is an isomerization reaction, and in presence of AlCl3, isomers of branched isomers of N-butanes are formed. So that should be the precise statement which I expected to be in the statement 2, but it is not there. Although both are true, I don't feel that statement 2 is the correct explanation of statement 1, and hence my answer will be B and not A. So very knowledgeable question in fact, and to tell you that don't just mark any random option. Think whether this is the correct explanation. First of all, guarantee that both the statements are correct or one of them is false, whatever, and then attempt the question. This is a very typical question in which most of the students get negative marks. So that's it for this lecture. I hope you have enjoyed this lecture. Please go through the previous question to this, which is on the potential energy diagrams. That is the most important question in the lecture, because that gives you a lot of information which will be helpful in your future. Thank you.